Hi, Owen.
Hi. Okay, great. We're live. Hey, got it. I consent to be in this meeting. All right. What's up, YouTube? Um, I'm here with my friend Markus Lohmeyer, who is a PhD student at pronounce your university.
Erlangen, University of Erlangen.
University of Erlangen. And I'm very happy to have him. Markus Lohmeyer works on Port Hamiltonian systems, and he comes at them. So I did my master's thesis on Port Hamiltonian systems from like a category theorist trying to learn engineering point of view. But Markus Lohmeyer is like a real engineer who has like the engineering and hardcore geometry chops to really like get into Port Hamiltonian systems. So I'm really happy to have him here helping me out. And today I'm going to give a bit of a tutorial to Markus on just sort of generically how to do expressions and interpreters, because Markus is working on a software system for Port Hamiltonian systems, which is going to use like a good amount of like symbolic programming. And so we're just looking to sort of get the, so he's just sort of interested in, yeah, what does it mean to have expression trees on a computer? How do you manipulate these things? How do you think about them? And this is something that I've done a bit of. So today, and we thought, hey, you know, this is actually a pretty general use. So we thought that other people might be interested in it. So today we're going to be live coding how to do basically just like simple interpreters in Julia. Yeah, so we might as well get started. So I think we're going to start with like a pretty classic example of that, like people start with when they're doing when they're doing like interpreters, which is we're just going to do a basic calculator. So this is going to be single typed. There's only numbers involved here, and just we're gonna expand on this, but for now we're just gonna like spit this out and get something running. So we're going to start with abstract type expra end. And this is going to be an abstract type that all subtypes of this we're going to think of as expressions. So what's the most basic type of expression? Well, a constant. So we're going to represent that as struct const val float 64. We're making this real simple. We're not doing any types yet. And so that's the sort of the leaves of our expression tree. Now we want to make some of the now we want to make some more complicated expressions. So let's say let's make an expression that represents adding two things together. So add has two fields. E1 is an expra and E2 is an expra. And already this is enough to start doing things. Oh, it doesn't like that because expra is already a okay, so I made several mistakes here. So first of all, expra is already a type in Julia, so that's no good. Let's make this calc expra, and then we have to make this actually a subtype. And this is going to also be actually a subtype. Okay, now let's try
line 18, line 9. Okay. Owen, still
yeah.
E1 and E2 calc expert as well.
Oh, yep. This is the joy of live coding.
Yes.
Okay, that works. And that works. Fantastic. So now let's just try this out. So we'll say E equals add const 1, add const 2, or 20, sure, why not? Const 5. Now we want to evaluate this. So let's write a function to evaluate this. Eval, well, when we eval a const, we just get e.val. And when we eval add, we get eval e.e1 plus eval e.e2. So this recurses through like a whole expression tree and evaluates it. So now if we eval E, what should we get here?
Oh gosh, I don't know, Owen. That's why we have a calculator, I guess. Okay, let's see, what did you type in there? 20, 26.
26. Yeah, all right, we did it. Cool. Okay, now we want to add multiplication. Marcus, why don't you add multiplication?
All right, I hope this will not affect the recording. Okay. Oops. It should be very similar.
Mm-hmm.
Is that fine?
Yeah. And then we can hit shift enter here. Oh, we have to shift enter here first, shift enter here. And then let's make this a mul. And what should we get here?
Gosh, I don't know, Owen. This is getting complicated.
101. Yeah.
Great.
1 plus 20 times 5. Okay, so that's all straightforward. So where do we want to go next? This is an honest question to Marcus.
Well, it would be great to have multiple types somehow.
Okay, cool. So what we're going to do is we're going to have multiple abstract types. So we're going to have a num expra and then a bool expra. And we're going to make this a subtype of num expra. I'm going to make all of these subtypes of num expra. Julia is not going to like this because we're redefining constants. So we're going to have to restart the, any struct is a constant. So we're going to have to restart the REPL after this. Yeah, we're pulling a JavaScript here by only having floats. But I mean, in scientific computing, who cares about integers? So let's see, how do I restart? Kill. And then if I just hit shift here, shift enter here, should it restart? Yeah. Oh. There we go. Okay, great. Run that. Run that. I don't know why that shows up there. So const not defined. What? Oh, there we go. Maybe we should use revise instead. Yeah, let's use, I'm sick of this VS Code crap. Quit this. We're gonna pull up a new terminal by hitting Shift Enter, but not evaluate anything. And then we're gonna run, terminal. Okay, yeah, that's fine. Then we're gonna, using revise, include, where are we? Okay. Include T, that stands for include tracked. So this will reload it whenever we make changes to this file.
Oh, and why do you use included, not include? I mean, what does the T do there?
I just said that it's include tracked, so it'll reload it.
Include. So include T is a special revise method.
Yeah.
Okay.
So yeah, exactly. So now if we save this file, and if we use like add, num expra not defined. It's defined right there. What's up with this? For num expra. Do I have a typo? Retry. What? What is going on here? All right, we might need to do a little snip here in post production. Revise evaluation error. Okay. We're gonna HP Julia REPL. We start the REPL just so that we have a normal REPL. We're in expressions using vise. We're going to go ahead and make this module expressions because this is, and then we should be able to do
just using expressions instead of included.
Yeah, let's try export const add null, and then we can just try using expressions. Okay, that worked. Now we can do E just like before, and then we're not exporting eval.
Yeah.
Because okay, everything's happy now. Great. Okay, so now we have bool expra. Let's make some bool expras. So first of all, how do we produce a bool? Well, we could produce a bool by checking if two values are less than or equal to each other. So we'll have struct lec bool expra, and then we can have LHS num expra, yes, num expra. Oh, right, we don't, oh, geez. Okay, well, yeah. Right, I don't want to hit lec. I don't want to hit Shift Enter anymore because we're using revise. So forget about that. So now we I'm so confused why that compiled. Okay, whatever. Now we can do E equals lec const for const 5. Yep, there we go. Eval E. Oh, okay, right. Expressions.eval E. What? Oh, I guess eval, because this is eval coming from
Base.
That's weird that this automatically, okay, I don't like that. We're gonna call this something.
Just call it E for short, maybe.
I don't like E.
Yeah, E, you have already, then just E, yeah, whatever.
Maybe evaluate. Yeah. Save.
But you have more evaluates on 27 and 28.
Yeah, right.
Yes.
Yeah, the fact that you can overload methods from core is cool, but sometimes it leads to problems. Okay, evaluate. No method matching evaluate like. That's what we wanted. So we have to write this. So yeah. Evaluate E lec equals evaluate E dot LHS less than or equal to evaluate dot right hand side. Okay, pretty straightforward.
Don't we need also an analog of const for bool? So like a bool value?
Yeah, we could do that. Yeah, so we could have struct const bool extra val equals bool. Okay. But this should be enough. Value E, true.
Yeah,
because
right,
4 is less than 5.
Right, because we are not wrapping the results in const again on.
Right. We're just returning normal Julia text.
Yeah, so that's why it wasn't necessary. Yeah.
So that's an interesting point. So there's evaluation, and then there's simplification. Both are things that you want. Both are things that you want to do in like in the context of like expression tree systems, because you might have like symbolic expressions which can't be evaluated all the way, and you might want to just simplify them. Yeah. But we're starting off with the assumption that you can evaluate everything to like a well-defined value. Yeah. So let's look at this now, and I want to give a alternate way of doing all of this, because at this point we're now sort of running into some duplication. Yeah, you can see we have const bool there. That's kind of annoying. It would also be kind of annoying to have an abstract type for every single thing that we wanted to do. So let's just wipe all. Do we want to wipe all this? Yeah, we can wipe all this, whatever. We're gonna wipe all this. Let's start from the beginning. And we're gonna start with abstract type sim expra, and we're gonna give it a generic parameter here. So now we can do struct const t extends sim expra t val t. And we can do struct add t number. Oh, we want yeah. So this is okay. So this won't allow us to do casting. That's fine. So t e1 equals sim expert t to sim t. So now if we write eval const equals val add equals that. Oh, we want to use evaluate.
Sorry.
So we don't conflict with evaluate e.e1 plus evaluate dot e2. Okay, save this. Let's export const add evaluate. Now we can do e equals add const 1 const 5. Oh. Invalid redefinition of constant const. Okay, we gotta restart this. Using revise, using expressions. Okay, now there we go. And now if we evaluate e, we get 6. If we instead did 1.0, 5.0, evaluate e, we get 6.0. If we did evaluate plus I, plus, im plus 0 im, we get complex numbers.
Right.
So our interpreter now has become much more flexible. However, we are now limited to only having Julia types in our consts, which could be that could be a drawback. One other thing that we could do would be to have we could have t be a symbol. So, or t could be something else. And then we would have here like val equals any. And then here, and then we do things more at runtime instead of using Julia's type system. Because when you use Julia's type system, it's convenient, you get a lot of things for free, but then you have to play with Julia's type system rather than doing things dynamically on your own. Yeah. So let's do some simplification, maybe. I don't know what would, or we could do, yeah. What should we do next, Marcus? What are you interested in?
Yeah, I mean, you just said like symbols and stuff. Like we were before talking about having some kind of types that represent different geometric spaces, like Euclidean spaces, or perhaps certain Lie groups and whatnot. And in that case, well, would it be necessary to go to the what you just mentioned, symbols rather than
Yeah.
Julia
Okay.
types? Do you think that's necessary, or is that why you brought it up?
Yeah. That. Okay. Let's do that. Let's do that. Let's try and write a language. Let's write a vector language.
Because that
So
will be more in the apps. Well, yeah, because that would be at the first level, that would be more abstract. It wouldn't necessarily evaluate to, I mean, in that case, we wouldn't be so much interested in writing evaluation, or at least not necessarily to start with. It's more important to build up the expressions and check that certain more complex signatures can only be forming an expressions if the types align. So I would be interested in seeing that type of application.
yeah, let's write a like a vector algebra system. That would be cool.
Yeah.
Okay. Or really like a tensor algebra. So we can have T expra as our sort of abstract type. And just to be, so there's probably, there may be like elegant ways of doing this in a way that's very integrated with the Julia type system. But let's do this very dynamically, because then we're not going to get bogged down by things. Like after we do it dynamically, there may be some clever way of integrating with the Julia type system. But for now, let's just do abstract type T expra. And then, so, okay, already from the beginning, we have a choice. So a expression of type T expra, should the dimensions be known as integers statically, or should we allow symbolic dimensions?
What do you mean exactly by symbolic dimensions, Owen?
Like for instance, do you want to only be able to have like 5x5 matrices, 6x6 matrices, etc., or do you also want to work with like n/n matrices where n is not necessary, is like a variable?
Oh, okay. Well, I guess we could go the second route.
Okay.
Let's see.
All right. So then let's have a abstract type dim expra end, which is like an expression that for yeah, dim. So, and then let's have two, for now, let's only have two types of dim expra. So you can have a constant dimension, or you can have struct symbolic dim expra name symbol. Seem reasonable? And now let's have constant tensor T extra val. This is going to be like array. I can never remember the order of the type parameters. Type of 1, 2, 3, 4. Oh, it's like, oh, okay. I didn't save this. I thought it was going to error there. Matrix array into. Okay, so we can have this be array float 64. Yeah, and then the it can be whatever dimension we want. So now we can define dimensions T const tensor equals map const dim size T. So let's test this out. So while I'm writing the right export statements, why don't you say what you think? Why did I just write this? What does that mean?
Good question, Owen. I was wondering indeed. Const tensor, you map would apply a function, but as a function you pass the constructor for const dim. And okay, so basically you're wrapping the dimensions, which are integers or a tuple of integers. Now you turn it into a list of integers, and you're wrapping them in const in this wrapper type const dim, I suppose.
Yeah.
Because that will be our type that defines if we can compose or contract rather tensors, I suppose. Something along those lines.
Right. So speaking of which, let's do a contract operator. So struct contract T expra. And now, so let's just, for now, we'll just have this be two tensors. So we're going to contract. So we'll say T1, T expra, T2, T expra.
Owen, wouldn't it be more logical, perhaps, because you can also contract one tensor? Wouldn't it be logical to just work with one field?
Yeah, it would. That makes sense.
And then have the product. So I guess we would need the product then somehow of tensors if we would.
Right. So we'll have a Kronecker product, I think. Yeah, we'll have a Kronecker product expression. That makes sense. Along, this is a dim x. No, this is not a. This should just be an integer. Right. Should we actually have this be a vector of integers? Because you might want to contract along multiple dimensions at once. Cool. Let's make it simple. We'll just have it be one. Okay, let's evaluate this. Let's evaluate the or we want to, right now the things are going to be we're going to simplify things. We're not necessarily going to evaluate them fully. So so first of all, because we're simplifying things, we can have simplify T equals T expra equals T. So by default, simplify does nothing. Yeah. But then opportunistically, we might take advantage of some stuff. So for now, we can have, we can simplify a contraction, and we'll say we'll say this is C, this contract. We'll make T equals simplify C dot T. So we'll try to simplify the inner bit. Now, if type of T equals const tensor, then we can do something else. Contract T C dot. So we try to simplify the inner bit. If we end up at a constant tensor, then we're going to simplify it further. Otherwise, we just return the result. Or otherwise, we like return what we simplified, but then keep the outer contract. Does that make sense?
No, sorry, Owen. I'm wondering right now what you mean there. Okay, first you say T simplifies CT. Hold on. C is our contraction and T is our underlying tensor. Okay, then why do you call simplify on T first on line 28?
So this is similar to how when we originally did the evaluate. When you evaluate add, first you evaluate the right-hand side, then you evaluate the left-hand side. Then
like this recursion into down the tree of expressions. Okay, so because T could again be another contraction or whatever.
It could be another contract, exactly.
Yeah. And then type of, so if T is a const tensor, which means we actually have numerical data, right?
Mm-hmm.
And if we, otherwise it's gonna be a, what did we call it? Symbolic tensor or something like this, right? No.
Yeah, well, it could be
what
another
would be the else case?
Or we could add, I mean, we might add other like subtypes of T-expra that it could be.
Yeah, and in that case, we don't do anything, right?
Yeah, because I mean, as we go on, we might figure out different ways. Like you might be able to simplify things that are not const tensors.
Right. But on line 32, it would be the same if you would just have written C, right?
No.
No.
Because we've simplified the inside.
Ah, yeah, right. Sorry. Yeah, clearly. Yes. Yeah. Okay, got it.
Cool. So now let's write this. I feel like there's some fancy schmancy function in Julia. I feel like some should be able to do this with the right. Yeah, I think if we just do const tensor sum T, C, sum
T dims equals
some result of calling. Oh no, okay, yeah, we don't. Okay, sum T dot val dims equals C dot 1. I think that should work.
Yes.
Right. Cool. So let's test this out. So dimensions simplify.
We have the contract.
Const tensor. We'll say 1, 2. 3, 4. Do it along 1. Oh.
I think you need to export contract. Is it possible?
Yep. Cool. Now we can try simplify E. Yep, that's right.
Great.
And now we can also write dimension. Let's put these like next to where they should be. So now dimensions, we can also dimensions see contract.
What are you doing right now, Owen? I didn't catch you. I guess what is the motivation at the moment?
We're defining dimensions for contract.
Okay.
So which is, even if we can't evaluate the contract, we may be able to still figure out what its dimensions are.
Yeah.
Even if it's like symbolic or something.
Yeah.
Specifically, there's probably a better way of doing this, but I'm just gonna make D equals copy dimensions C dot T delete D C dot along D. I think that you can use delete in that way, but I'm not sure. 2, 3, 4, 3. I should make this. No. Okay. Julia, how do you delete something? How do you remove an index? All right, Google. Julia, remove element from list. Julia.school. Jesus. I just want Julia docs. Docs.julialang.org. Vectors. Base.vector. Should probably be in the same place as push. Base.push. Okay, push pop at. There we go. Oh, well.
Yeah, there's also delete at.
Oh, okay.
It's just at. You just need to add at.
Add a to a. Okay, great. Pop that. Pop it. Okay, great. So yeah, basically we just the dimensions of the contracted tensor is the dimensions of the underlying tensor minus the dimension that you're contracting along.
Yeah.
Cool. Should we do the Kronecker product? Actually, before we do the Kronecker product,
I'm just wondering right now on line 20.
Identity tensor. But yeah, sorry, what?
This D you didn't wrap. Oh, well, hold on. I mean, didn't this you don't wrap in const dim, do you?
This,
You would
it's
have
already wrapped in const dim.
but const dim is a is an integer, vector of integers, right?
Let me show you. So yeah, E is this.
But then you don't unwrap it in dimensions, right?
Yeah, I mean it works fine.
Can you scroll up a bit, Owen, please?
Yeah.
Just to see where const dim is defined. So you call it n. Okay. So don't you then need to put on line 31 d.n?
Dimensions returns a vector of dim expressions. So like, yeah, D is a vector of dim. I don't know why it thinks D is an integer.
But on line 22, Owen, on line 22, you say you want to compute dimensions of a tensor. You did the wrapping in const dim, right? You take the dimensions of the array and you wrap it in this const dim.
Yeah.
Ah, okay. Now I get it. It's a yeah. We are deleting this one const dim thing. Yeah.
Yeah.
The array. Yeah. Sorry. I had the wrap. Yeah, I switched up the two levels of list and wrapping. We don't wrap lists. We have lists of wrapped integers. Yes. Okay, makes sense.
Okay, I think actually the next one that we should do is the identity. Or rather, more generally, delta. So right. So function struct delta t extra. This can be the k int and then dim extra. So it's going to be like dim by dim by dim by dim, like k times. That's the identity.
Okay.
So
yeah.
The dimensions delta equals dim for dim for blank in k. G dot k. Yeah. We can contract the identity. We can contract delta. When you contract delta, you just get another delta. So I think we get delta t dot k minus 1 t dot dim. It doesn't even matter what we're contracting it along.
Yeah.
So let's test this out. So E equals contract delta. I gotta export delta. Contract delta, let's say 5. constant. Or let's use a symbolic dimension just for fun. A n contract. Oh, we forgot. No, delta is a t. Oh, we got to contract it along something. There we go. Simplify e delta 4. Perfect.
Yep.
I think for our last trick, let's do the Kronecker product. And then let's simplify a contraction of let's simplify a contraction of a Kronecker product without computing the Kronecker product first. Because oh wait. No, do we want the Kronecker product? No, we want outer product. Outer product, that's what we want.
Yeah.
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 Because that's like when you contract the outer product, that's how you get like matrix multiplication, for instance.
Yes.
Though the that's gonna wait. Okay, when you take the outer product of two matrices, you end up with like 4-dimensional tensor.
Yeah, that's not really what.
Something. But that's not actually what you want, because you want to be, you want two of the indices to match up. You want to be contracting a 3-dimensional, a 3-tensor.
Well, if you get a
So what's the operation we want?
I'm not sure, but I guess it's fine to have a 4 tensor and then contract these two.
No, because at some point you need an actual multiplication.
Yeah. I guess this contract that we defined is not the contract that I was thinking about it with. I mean, this is really just a sum along. I mean, the sum along a certain dimension isn't never going to give us a matrix.
Oh, right. Right.
Really,
maybe that's not what contract is.
We didn't really define the contract that we meant to define, I guess.
Contract is like, is there like there's there like a multiply in contract normally?
Yeah.
Oh, I know what it is. So I think typically what people think about for like contracting is that like they have up indices and down indices, like primal indices and dual indices, and then you pick a primal index and a dual index and you contract those two.
Yes.
Okay. So we could, so that, you know, up indices and down,
So we need to define the contract object. The contract struct needs to hold two things, and then only if the two things are the same, then it's going to do, I guess, what you implemented. Is that correct? I'm not sure.
I think that, right. Okay. So one way of doing this would be to say, okay, we'll give contract 2 dimensions,
Yeah.
and then it like it sums and multiplies. Yeah. Yeah. Wait, it multiplies. Right. It like somehow has to do a sum and a multiply.
Yeah.
It multiplies them together and then sums them.
Yeah.
Right. But the other way of doing it would be to have like we could have our tensor expression, instead of having dimensions, we could have up dimensions and down dimensions. Or like up dims and down dims. And each it would have up dims and down dims, and then you could just always rearrange it so up dims came before down dims. I mean, I guess, well, okay, because you could have like an actual const tensor that had like interleaved up dimensions and down dimensions. So you might want, anyways, but then you could like contract, you could pick an up dimension and a down dimension.
I can see, Owen, how you could nicely define a I mean how that could add some more information, but do we really need this right now? Wouldn't it be, I mean, that would be one, to me it seems like that would be one extra step to make it to differentiate between up and down indices. At this point though, I guess anyways we need to have a different notion of contract, right?
Well, okay, now I'm actually conflicted again.
Because you cannot just contract.
Because I feel like we should be able to simplify this out into like 2 steps. Like there should be a multiply step and then a contract step.
Multiply in what sense?
Like, okay, you have 2 matrices, and then you take their outer product.
Yeah.
Now this is a 4 tensor.
Yes.
And each, right, yeah, no, okay, right, when you take their outer product, I got confused. When you take their outer product, each element in their outer product is already a multiplication. And then you contract. You contract. Oh. No, you take a here's the step that we're missing. A diagonal. You take a diagonal and then you contract. So you like you take a diagonal so that you get those indices to match up. Like in you'd write it like a sub I to the j, b in like Einstein notation to the k. And it's like these, you're like multiplying along these indices.
Right.
And what ends up happening is you have you take the outer product, which has like the outer product is like a 4 tensor where the elements are this.
Right.
Then you take a diagonal of the outer product, which is a 3 tensor, where the elements of that the elements of that 3 tensor are this, and then you contract and you get a sum. Sigma. There we go. Yeah. Yeah. Eventually you get, so there's 3 steps: outer product, diagonal, and then sum.
Okay. Yep.
Okay, do we want to do these? Let's do it. Let's do it. Okay. So first, let's do the outer product. Struct outer product T expra T1 T expra 2 T expra mentions T outer product equals dimensions T1 T1 concatenated with dimensions T2. Yeah. Now struct. I'm gonna call this re-indexing. I don't know, that's a terrible name for it probably. But we have T equals T expra, and then dims vector int. And I'll show you, and I'll tell you what this is like doing essentially. Basically dimensions re-indexing equals T dot T, and then D sub I for I in dims. Set. So this would allow you to permute, but also, but is that quite right? No, we need something else. 2. We need index map. Oh, because this could be really complicated. Like in general. Because in general, like this could be like an arbitrary view of a tensor. So we want something we want something simpler for now. Let's just say struct diagonal and this is going to be like long int.
Owen, don't you need to
assert d sub I equals d sub I plus 1.
Oh, okay. So now you're assuming that the 2 are neighbors, right? Because I was wondering,
right.
Why wouldn't you have I and J like instead of
Okay,
along,
yeah.
right?
Yeah. Yeah, that's a better way to do it. So d t sub I t sub j, and then the dimensions here.
I guess, okay, no.
Where should we put? Maybe we should delete t. Maybe we should delete at t dot I and delete at t dot j, and then put the dimension in the front. At d t dot I. Oh no, it's gonna. Ah, God.
Oh yeah, okay, now I see.
I hate mutation.
Yeah. No. This is also not nice, not nice. Oh gosh.
If you delete the first, yeah.
Crazy. Good idea though.
Okay, that's a little janky, but okay, I don't know if I want to simplify this, but then basically, so like a matrix multiplication now would look. I just want to write out what a matrix multiplication looks like. Delta outer product diagonal. So it's like if we make like A equals tensor 1, 2, 3, 4. Re-indexing.
Yep.
Diagonal. Let's do actually. Two dimensions A, B. Oh, that's no good. There we go. Okay. Now, mul equals contract diagonal outer product A, B. Diagonal should be along. Oh God. It's the dimensions of A are 1, 2. Dimensions of B are also 1, 2. Oh shoot, that's no good. Wait. This should. How do we get? I just want. Okay, whatever. We're gonna do. We're gonna have this be 1, 1, just so it works out. Okay. Dimensions B. Okay, dimensions A. So, okay, mul equals contract diagonal outer product A B diagonal 2 3, and then we're contract, and then the diagonal puts the dimension at the beginning, so we're going to contract along 1. Okay, now mentions mul. Hey.
Could be right.
So we got the right dimensions. So maybe that yeah, this is already a pretty long video. So maybe we can close for now.
Yeah.
Yeah, you know, I don't have much quality. I don't aim to produce like the grabbiest, showiest, edge of your seat content. So, you know, this may have been a somewhat humdrum video, but you know,
Sure.
Hopefully people like put it on when they're doing something else. And I, you know, people tell me to keep making these videos, and I feel like sometimes they're kind of boring, but whatever. Maybe someone will like this.
Sure.
So yeah. Anyways, if you stayed until the end, my loyal viewer, I thank you. And I will see you next time. You can stop the recording now, Marcus.
Yeah. Thanks. Thanks, Owen, for showing me.